Hello. Hi guys. I hope that it is nice and good. I don't see much people, not sure if the people know that the stream is for 11, not 11:30, because like earlier it was like 11:30, but I have to actually go out. That's the reason I have to prepone it to 11. Not sure that folks are here or not. If anyone is here, I guess no. Can you please say hi, hello, something like that, and we can know that people are here, or else shall we start the stream at 11:30 only? Anyone here? Not sure that. Okay. Udit Mehta. Hi Aryan. Hi Udit. How was the contest for you? And yeah. We see the people here. I guess people are here. So yeah, whosoever comes in, Money, cool. Hi, Money. Not that high. Yeah, hi. And yeah, the folks coming in, please do let me know who all are coming. Suraj is back here. Hi, good morning. Very good morning, Suraj. And yep. So shall we start with the problems itself? Yeah, let's go. I guess the folks don't know that it's of 11. Like, just for you guys to know, it was of 11:30, but I have to go somewhere. That's the reason I had to prepone it to 11 rather than 11:30. But yeah, folks are joining. We have less viewers right now, but we will see. But yeah, let's start with the problem. Shanka, hi, good morning, bro. Let's start. Let me quickly switch my stream. And hey. Yo, now, let's see. So, okay, it's not visible though. Let me quickly switch back. I guess it is visible now, right? So let's start with the first problem itself. Yeah, if you guys have not liked yet, we are gonna see all 4 problems. So yeah, let's start and let's see. But yeah, before that, please do smash that like button, because we're gonna see all the problems right now. And starting off with the first problem itself, it was pretty easy, but a bit like kind of longer than the original problem is. I love coding because of you. Love you, bro. I love you guys. See, let's move on to the first question. Determine the winner of a bowling game. So what the problem says is that we are having 2 zero-index integer arrays. So we are having 2 arrays called as player 1 and player 2. Right? That represents the number of pins that player 1 and player 2 hit. So basically in a bowling game, player 1 and player 2 are playing a bowling game and they hit some pins. So number of pins they hit in particular time that it is told. The bowling game consists of n turns. So in one turn, how many pins they strike, that is given. And the number of pins in each turn is exactly 10. Number of pins in each turn is 10. That's standard, right? Assume that the player hit xi pins and in the ith turn, and the value of the ith turn for the player is nothing but 2 into xi when the player hit 10 pins in any of the previous 2 turns, which means if in the turn right here, ith turn, if he hits, let's say, xi pins, then it will become 2 into xi if in the last turn he had 10, or in the second last turn he had a 10. As simple as that. The score for the player is the sum of values of their n turns. Now what we have to tell is, we have to return one thing. 1, if the player 1 has a higher score. 2, if the player 2 has a higher score. 0, if both have same score. So what easily we can do is, we can find the score of player 1, find the score of player 2, then just compare. Okay, player 1 score is, let's say, this, player 2 score is this. If player 1 score is more, I'll return a 1. Player 2 score is more, I'll return a 2, else I'll return a 0. Now the task is to find the score of the player. We will do exactly same what is mentioned in the question. We have the pins they hit, Now I need to find the score. The score, it can be xi or xi into 2, right? 2 into xi. Xi will be, in normal cases, 2 into xi will be only and only when the last one strike was 10 and the last second strike was also 10, or 10. So like either the last one or the second last one. If any of them is 10, I'm gonna say, okay, the score right now is 2 into xi rather than xi. I'll do the same stuff, which means for the player 1, if you see right here, player 1 has strike count as 4, 7 and 9. So basically right now the score is 4. Here the score is 10 because I'll just see the last and the second last to actually increment. Here I will see 7. Okay, for sure the score is 7, but as soon as I look back, I can easily see that my last score was 10. So now its score is 7 into 2 rather than only 7. So its score is 7 into 2. He will ask 9. But if we look back, okay, it's not 10, no worries. But if we look more back, which means second last, it is actually 10. So its score is 9 into 2. That's the reason if we just sum this up, 4 plus 10 plus 2 into 7 plus 9 into 2, that is nothing but 46. That is the answer, 46. Let's look at the next one. Although it's very easy, we can just say that 8, 10, 10 and 2. Now, if you just look, okay, it's a first element. I can't look last or not even second last. So it is just score is 8. Here the score is 10, but I can look last, but I cannot look second last, right? So I can't look there. Cool, no worries. Here I will just say, okay, the score is 10, but I can look last, and last is actually 10. So basically, I will just look at, if I'm starting at I, I look at I minus 1 and I minus 2, provided I can go to I minus 1 and I minus 2, right? So it will be 10 into 2, it will be nothing but 2 into 2, because last one is 10 and also the second last is also 10, so but I want just one. So I can just add the score of player and I'll just count the scores of both the players, and that's pretty much it. We can just give out. Now constraints are pretty small. We can just iterate on the entire array, find the score of both the players in O of n time. Basically, we have n of those what they say, n turns, right? And n is very less, 1000. So that can easily be done in O of n, and we are good to go. So you guys know that what we have to do. We have to iterate on this player one's array. Then we have to find out, okay, what is the score? To find out the score, I will do, okay, for the current element, I will look at the last, which is I minus 1 and I minus 2. But for the first element, which means n equal to 1, I have no I minus 1. For the second element, I have no I minus 2. So I have to just have the edge case that, okay, just consider first element separately and second element separately. Then after that, you can just go and check for I minus 1 and I minus 2 for every other element from I equal to 2. Let's quickly code that up. But yeah, before that, if you guys are watching it and have not liked it, then please smash that, spank that, whatsoever you want to do, squeeze that, die that, anything. So if you just look at the code, that's pretty easy. Firstly, I just named player 1 as P1 and player 2 as P2 because it's hard to write that player 1, player 2 again and again. Now it is that I just have this S1 and S2 as the sum of player 1. S1 is the sum of player 1, S2 is the sum of player 2. Then it just say, as I said, for the first, when n equal to 1, I can't check back or like second back, which means last or second last, I can't check. That's the reason I have this one case. Okay, if n is 1, just only check the current element only. So the score will be added only for the current element. No conditions to check if the last one was 10 or the second last one was 10. No condition for that. While in the case when n equal to 2, so now at the second element, I can check if the last element, which means if I am standing at the second element, which means I equal to 1, so the last element will be I equal to 0. So it will just check, okay, if it is a 10, so just have a score of 2 into P1 of that, right? If I am at I equal to 1, hi to all the folks who are here. If I am like, it is I equal to 1, right? Here it is I equal to 1. Here it was I equal to 0. Thus, I will just check. I equal to 1. I can check for I equal to 0 also. If it is a 10, then I need to do a 2 into that score of that particular index. But I can just add that again or do it 2 into, both are the same things. Here also for the player 2, I will just check if the last one was my 10. If it is, then I'll just add a 2 into. Now comes the interesting part, that I starts from 2, which means I will start from the third element itself. Now, what will happen now is, at every point I will just check. For P1, for the player 1, I'll just check if the last score was 10 or the second last score was 10. If the last score was 10 or the second last score was 10, then I need to add a 2 into pi, else I'll just add a pi. For the player 2, I will also check the same condition. If the last and the second last is 10, add a 2 into pi, else add a pi. And at last, if this S1 score, which means player 1 score is more, return 1. Player 2 score is more, return 2. Else, if it is both are same, so return a 0. So yeah, that was first question. Now let's quickly move on to the second question. But before that, let's have some quick chat read. Yeah, let's start. Good morning, Aryan. I love coding because of you. Love you too, bro. I am excited to know how about second problem. Cool. We are going on to second problem right now. Second is easy. Yeah, correct. How are you? I'm super cool. How are you, Pratham? And MS Darshan is here, right here. Hey Aryan, yeah, yo bro, hello Akash, hello. Pratham, MS Darshan, Suraj, Shankar, Mani, Udit, everyone is here. Bennett, how you have time for DSA while you are working? That's a good question, but we will take that in the last. But yeah, that is what you guys make me do that, because you guys love what I do. I love because of you guys that you support. If you were not there, if you would not have been supporting, that would not have been possible. But before that, can we reach to 20 likes? Can we? Just smash that, and let's move on to the second question. Just smash that. If you're new in the stream, you can also subscribe, but that's when you watch the stream later. But for now, just like to banta. It is valid. Now moving on to the second problem of our first completely painted row or column. Cool. Now it says that you are given a zero index integer array called as ARR and an m cross n matrix called as mat. Cool. Having integer array ARR and an m cross n matrix called as mat. Now, ARR and mat both contain all integers in the range from 1 to m cross n. So basically, you can consider n numbers from 1 to m cross n. So basically, the matrix itself has all the numbers from matrix sizes from 1 to m cross n. So it will contain all the numbers from 1 to m cross n. Cool. Now comes, okay, go through each index of I in array. So basically, we have to just implement the same stuff. Now see how. Go through each index I in array starting from the 0, which means I'll just go on in the array from left to right and paint that cell in mat containing the integer ARRI. So I'll just say, okay, what is the ARRI value? Then I'll just paint that ARRI in my matrix as some color. Blue. Cool. Return the smallest index I, which means in this array we were iterating from left to right, right? So smallest index I such that either a row or a column, any one of them, either a row or a column will be completely painted in this mat. Let's look at the example to get the clear understanding what it says. So basically I have this array called as 1, 3, 4 and 2, right? Now I will just iterate on this array from left to right. For this one I'm standing here. So what I'll do is I'll color this matrix as 1. Now okay, this is colored right now. Cool. Let me color by pink. It will be visible. Okay, it is colored right now. 1 is done. Next, okay, now I will check again. Is any of my row or column completely colored? No, like no one right now. So no worries. I'll move on to the next element, which is 3. I will just color that. Now both of them are colored. 1 and 3. Now again I'll check. Is there any row or column which is colored completely? We can't see. Cool, no worries. Go on to the 4. Next element. Again I colored that. Now I asked you again. Is there any row or column which is colored completely? Yep, we can see this row. We can see also this column. So basically I have found my smallest index I such that my at least one row or one column is colored. Now I can return this index which is I equal to 2 and it is my answer. Let's look at the next example. It's very same, that we have this array 2, 8, 7, 4, 1, 3, 5, right? I was starting at 2. I'll just color it. I'll just check because I need to check at the smallest index I, right? Before that, please, if you are just watching this and you are liking this, because we're gonna see all 4 problems right now and here, then if you're just watching it, then please do smash that like button. Let's reach to 20 likes. It's just 18, just 2 more, that would be good to go. So now we are at 2, right? Okay, I'll just say I want the minimum index of this ARR such that one row or column becomes colored, completely colored. 2. 2. I just colored that. Any row column got colored? No. I'll just color next element which is 8. Now any row column which got colored. Now I color next element which is 7. Any row column which got colored. I'll color next element which is 4. Colored 4. Oh, you will see this column right here got completely colored. I will just say, okay, I found one column at I equal to 3, 0, 1, 2, 3. I equal to 3, I got found one column that is completely good, that I will written I equal to 3 is my smallest index in my ARR to actually just give that answer. Now you will say, Aryan, that looked pretty easy. What we can do is, as you were saying, that we can just iterate on this entire array ARR, and I'll just iterate on this entire array ARR which is 2, 8, 7, 4, 1, 3 and so on. I just iterate on this, and at every point, which means at I equal to this, I'll just check in my entire matrix if any row or column it became completely filled. I said, do you think it will work? I mean, it will work, but the time complexity, the array size itself is n, where n is nothing but r m cross n, and m cross n size is nothing but 1e5. So its size is 1e5. And when we gonna check in this entire matrix for every index, it will also take m cross n size. That's not gonna happen, which means m cross n into m cross n, which is 1e5 into 1e5, 1e5 into 1e5, 1e10. That won't work. But I also know one thing for sure. I need to iterate on my array ARR for sure. I need to iterate because ultimately I need to find the smallest index of ARR. So for that, this m cross n of ARR, this complexity will not reduce. But can I reduce something which I was searching? Which means I was iterating on this array, and then I was just searching for this element, right? Okay. When I added this element in my matrix, let's say at this position, is any of my row or column became completely colored. So I was just using that m cross n. I know, okay, I can't optimize this thing, but I also know maybe I can optimize this, which means now I am thinking I need to find any row which get colored after I add an element. Oh, completely colored. If you just look back at it carefully, then you will realize one thing. What we see is that at every element added, how you know that a row is colored, completely colored? Without actually iterating on the entire row, how will you know that the row is completely colored? If the color count of this particular column, if it got 3, see, we can maintain something like this, the color count, or for rows and for columns. If this color count of this column became as the number of rows, which is 3 actually, so what will happen? I can just easily say this row is colored. Thus, what I can do is, my aim was to actually find, okay, if any, after adding an element, which means coloring any element in my matrix, if any of the row or column, if it became colored, then I have to just mark it. I have to just show it. But what we can see is that to actually know if any row or column got colored, I don't have to iterate on the entire column again and again. I can just maintain the count. Okay, how many columns have been colored so far? As soon as the count reaches the number of rows. For the column, the count reaches number of rows, and for the rows, the count reaches number of columns. For the rows, the count reaches number of columns. So basically in this you can see the number of columns, the number of cells colored are 3, which is actually number of rows in this entire thing. So I can just say, okay, Aryan, as soon as my color count of any of this reaches 3, which means number of rows, I'll just say I have found a column which is colored. That's it. That is the whole thing. Which means that at every addition of an element, which means I'll just maintain two things, two very basic stuffs, which means a column and a row array, which means it will maintain, you can see the left one, it will maintain the color count of the rows and it will maintain the color count of the columns. As soon as I add an element right here, what I will do is I will increase the color count of this to 1 and this to 1. How I will increase? I know its index, right? I comma j. I know the index I comma j. I can just go at this particular j and go at this particular I. Here you can see I comma j is nothing but 0 comma 2, 0 comma 1, sorry. So it is 0 1 2, 0 1 2. Then I can just go on to this and increase the color count. Now next what will happen is the same thing. As soon as it reaches here, next element when it is added, so 8 is added now. Earlier it was 1. Now when 8 is added, so I will just increase the color count of this particular column and this row also. Now okay, it's updated. Now as soon as the 7 is added, what will happen? Just look at this now. What will happen is my earlier color count was 1 1 1 1, sorry, 1 1. Now as soon as the 7 is added, the color count will increase by 2 for this, just increasing my j, and here the color count will increase by 2. Now by this, when the next last element, which means the next element is added, it will just again see, okay, whenever 4 is added, now the color count will increase by 3 of this cell and it will increase to 1 for this cell right here. As soon as the color count reaches for this particular, which is at the top horizontal one, it represents the color count of the columns, and the color count should reach the number of rows because it is 1, first row, second row, third row. For the column, the color count should reach number of rows. For the rows, the color count should reach number of columns. As soon as the color count reaches that number, I can just say, hey, I have found this particular index. This particular index right here is that index which have actually one row or column which is colored. Before that, please folks, let's reach to 25 likes. You guys are 26 right now watching, and how we can just not increase the like button. If you're liking it, just smash that like button. Play boxing with that. Meanwhile, I'm just explaining to you. Don't get tired because we need to understand also. But yeah, just play boxing with that like button. Now, what will happen is, the issue what we were having was that for one number, for this particular index, I had to iterate on my entire matrix again and again. But now I don't have to iterate on that again and again. I can just maintain this particular sum column and row, which will actually keep on updating as every element keeps on adding. And how we'll update? By our index I comma j. It is nothing but j, it is nothing but I of that particular array, which is a linear array right here. Now, as soon as any of this value, as I am updating, any of these value reaches my, if it reaches the number of rows, let's say number of rows are n. If it reaches the number of columns, which is number of columns are m. As soon as it reaches this number, I can just return, okay, I have found this index and this is the answer. And it will work in O of m cross n time capacity, which is nothing but 1e5 only. That is how we will do this. Now let's quickly code it up. Just quickly have a chat, walk through how to think about applying BFS Dijkstra or DFS plus DP in third. Got a TLE with DP, yeah, correct, it will get a TLE. Bi-weekly fourth question when? Bi-weekly fourth question when? Yesterday we had all the 4 questions for bi-weekly. If you have not watched it, then do watch it. Yesterday's stream, we had it at 11 p.m. till 1 p.m. I guess, yeah. Hinge, are you checking the negative index of an array? Okay, solve first question, please. Maybe the problem appears. Okay, create a row, column, vector. Correct. That's correct. Hinge, we can make a row and column. Correct. Are the numbers in the array distinct? Kishan, yes, they are unique. I will give you the code, please. Tell me any handle. Hinge, you are giving the code by pasting submission result URL. How will you search that for that element in the matrix? How will you search for that? Yeah, for that we can just take and map, because no, we know the elements are distinct, right? So for sure, if I need to find, okay, if I will just iterate on my matrix, firstly, I will just iterate on my matrix from here, then I will just say the actual location of 3 in my matrix is 0, 0. I will just map my 3 with its actual coordinates. Location of 2 is mapped to 0, 1. Location of 5 is mapped to 0, 2. And by this I will map the entire matrix initially. Now as I move on to my element, which is, let's say I move on to 2, I just ask my map, hey map, what is my index, what is my coordinates of 2? My map will return my coordinates of 2 as nothing but 0, 1, which is a pair of int, int, and by this I can go back to my matrix to actually know, okay, it is the element at this location in my matrix. So with the help of matrix itself, I was just identifying, okay, hey, just let me know what value at what location you are present, and then after that, when I'm going to iterate on my array, I know all the elements are unique, then I can just easily go and iterate on that. That's how we will do it. I guess you got that thing. Yep. Use another map. Yeah, correct. We can use another map. That is better because maps will be have O of n log n. But yeah, if the folks are watching and not liked it, let's reach to 30. And now we will see the questions, the code explanation of this particular problem. Let me quickly switch back. If it is visible. Okay, cool. Now let's see. It's pretty simple. As I told you that firstly I will have my initialization of n and m, number of rows, number of columns. Then I will have a row vector which will actually say, okay, what is the count of colored elements in my first row, second row, third row, fourth row. My column vector which will keep the count of colored cells in my first column, second column, third column, fourth column. Now I have this unordered map as who was saying? Yep, Akash. Just as Akash was asking that, okay, how we will have this. So it is, we can take this unordered map to actually keep, okay, for this particular element right here, which is actually in my entire array ARR, then what is the location of this element? It is I, j. So I will just iterate on my entire matrix once and will just keep, okay, for this map of one element, I'll just map it with the coordinates, I, j. And that is how I mapped it. Now, when the mapping is done, now I'm good to iterate on my array ARR. I'll go and iterate on my array ARR. For every element of this array ARR, I will find, okay, what is the row and column this element of array ARR is present in my matrix. So I will just get the row and the column of that element in my matrix, because I need to actually know the location of that element in my matrix, because I need to color that cell, right? That's the reason. I just get the row and the column in my actual matrix, and then what will happen is row will just increase by I just have that row array, right? Row array and column array. So row array, at this particular row, it will increase by row of r plus plus by just saying, okay, one cell now is colored more. Here it will just say, okay, one column in the column array, which is this calls array, it will just say, okay, this column array at this particular column C, one cell is colored more. And when I am done coloring this cell, I'll just check, hey, is that cell which we have colored right now, rows of R, has it got all the columns colored? If yes, please return that particular index. Or if that column of my particular columns of C, has it got all the rows colored? Rows is number of rows is n. Has it got all of them colored? If yes, then to return a index. And ultimately, if no matter what, if it can't, then you can return a -1. So yeah, that was question 2, folks. Let's smash that. Let's reach 30 likes and we would be very, very, very happy for that. Let's reach to the next problem, which is problem 3. That was problem 4 was easier than problem 3. You know that. I don't know how, but problem 4 was more easier than problem 3. I don't know why they had to do such a great thing, but many folks just tried for sure. That's the reason it would have just gone that way, that it has more submissions, but actually problem 4 is much easier than problem 3. Now, thank you. Use got it, Hinge, no problem. And using a map gives us O of 1 time complexity, which is way more better than scanning through the matrix with O of n square time complexity. Okay, giving a map gives O of 1 time complexity. How O of 1? You have to anyway get iterated on the matrix, right? Got it. Please explain third question. Yeah, third question is right here. Bro, first explain problem 4. Problem, like we'll actually move on the order as the ranking was saying that, okay, how we actually move on the order. But we actually see problem 4 also. That's no worry is that, now let's see how it is done. The problem says that minimum cost of a path with special roads. Understanding this problem is important, and also the constraints, that what all we can apply and think. Now see, we are having a start. Before that, if you guys have not, arey yaar, 30, I just said 30 bahut pehle. Just do that 30, just one remaining one, and we can have that. But meanwhile, let's start with this third problem that we are having an array called as start, and which is nothing but the start coordinates of my cell. Cool. I am also having an array called as target, which like is start within the start location, which is the initial position, as it is saying. Okay, it is the initial position, and in a 2D space or 2D matrix or a grid, anything whatsoever you can say that. Now you are also given the array as target, where you have to reach this target. Now represents your target position, target x comma target y. The cost of going from a position x1 comma y1 to any other positions in the space, which is x2 comma y2, is nothing but mod of x2 minus x1 plus y2 minus y1, which means if I had to go from 1 comma 1 to actually let's say 4 comma 4, then the cost to go from the 1 comma 1 to 4 comma 4 will be nothing but 4 minus 1, which is 3, 4 minus 1, which is 3, 3 plus 3, which is 6. Nothing but ABS, absolute modulus of this particular thing. Now there are also some special roads. Okay, what is special road like? You are given a 2D array called as special roads, where special road is nothing but the road from x1 y1 to x2 y2 to x2 y2 with the cost of I. That is a special road given to you, which means although you can move from one cell to another cell, just as if like you have your matrix. I will just erase that. It's a rough work which I did. I just erased that. So like I just made in my entire matrix and all that stuff in this particular board only. So now the standard normal way is, if we have a matrix, right, to move from the cell right here to cell right here, it's just say, okay, the cost is nothing but 1, because it is the coordinates are 0, 0, it is 0, 1. So to move to adjacent cells, my cost is always 1. My cost is always 1. Cost is always 1. Cost is always 1. Cost is 1. But you can see, if I just try to go from the cell x1 comma y1 to x2 comma y2 via just adjacent movement, so actually the cost incurred standardly would be x2 minus x1 plus, considering x2 is more than x1, like have ABS everywhere you do, you see I do a minus, right? Plus y2 minus y1, and still it's a ABS. It will be the standard cost, but it is saying, okay, what if I give you a better path with a better cost? That will be that cost of I. It can be better, it can be worse. Just make sure. But it's giving you an extra, okay. It's just extra, something extra for you. Now, what will happen here Next thing which it says is, it indicates the ith special road can take from x1, y1 to x2, y2 with a cost equal to cost of 5. You can use each special road any number of times, although this is stated, but it's redundant because it's of no use to actually. I got scared while the door closed. But yeah, before that, if you guys are liking it, then please do smash. Let's reach 35. Problem 3 question, easy question for people who watch. Yeah, correct. That is correct. That was super correct because it's just intuition, that what you get to know and how you think for a problem, right? If you have watched a bar graph series, like we just say, okay, how in the matrix we can visualize the graph is being made, that initial thing, how to visualize if it's a graph problem or a DP problem, that initialization or visualization of the initial thing itself will actually direct you. Okay, you have to think in the graph way or a DP way. Now let's go. With a cost equal to cost of I, you use each special road any number of times, although that is written, but it's of no use because it's written minimum cost required. So why to use same path again and again, right? Minimum cost, traversing on a path will incur a cost, so that is a redundant thing, but yeah, still we can consider that. Return the minimum cost required to go from start x to, which means start coordinates, to the last target coordinates. What is the minimum cost? Now let's look at the problem right here. Now for this problem visualization, I have made the matrix. So it is how I visualized in the contest itself, that it was given that, okay, you have to start from 1, 1 and you have to reach 4, 5, right? Special roads are given. We will see, okay, what's the special roads like, but right now it was given. It is a 2D space where you can move from one cell to next cell, and it is the cost incurred, which is ABS of x2 minus x1 plus y2 minus y1. I just did the same thing. I need to reach from 1, 1 to actually 4, 5. Right, I just made the matrix of 5, 5 cross 5 size. Now the standard path is, okay, to move from here to here, the cost will for sure be 1. To move from here to here, the cost is 1. To move from here to here, the cost is 1. To move from here to here, the cost is 1. To move from here to here, the cost is 1. So it is a standard cost of movement. Now the problem is saying that I have some special paths, which means from 1, 2 to 3, 3, I have a cost of 2. Shall I take it? It is saying from 1, 2 to actually 3, 3. If I had not taken it, then I would have incurred a cost of 1, 2, 3. I mean, I would have incurred the cost of 3 to actually move like this, right? But I have given a special path which can actually move it in 2 steps. You can see in 2. So it is actually helpful for me. I will use this thing. Okay, from this orange path, you can see I can move in 2. Or if I would have not grabbed this particular edge, then it would have moved in 3. So it's good. Okay, I'll just have it in my answer. But yeah, I'm just thinking, okay, shall I grab it? Shall I not grab it? Next special edge is from 3, 4 to 4, 5 with a cost of 1. Let's see if we should take it or not. 3, 4. Let me erase this. 3, 4 to 4, 5 with the cost of 1. If I would have not grabbed this cost, then one option would have been for me is go left, go right, go down. One cost. Cost incurred would be 2. But it is giving me that same thing of movement in one cost. Okay. Now I get to know one thing. I have a cost to from 1, 2 to 3, 3. I have a cost of 2, which is a good cost. From 3, 4 to 4, 5, I have a cost of 1. Okay, that's also a good cost. Now, my ultimate target aim was to actually reach from 1, 1 to 4, 5. Thus, what I will do is I can have multiple hops. I can go from here to here. I can also go to any cell, any other cell also, like which is adjacent, because it is saying, okay, how I can move. I can move adjacents, like in the adjacent cells. Now, what will happen here is I can go here, I can go also here. If I just go here, 1 cost is incurred. From here, I can go anywhere. I can go right, down, left. I can't go because I have already gone left, so it's of no use to go back. The cost will increase for sure. But before that, folks, yeah, you are not liking, you are not smashing. If you are liking it, then do smash that like button. Let's reach to 35. And with that, we would be solving that question. Now, from 1 comma 2, I can go anywhere else, but yeah, still, let's say I choose this path. The cost incurred was 2 here, 1 here, 2 here. Now from 3 comma 3, I can go to adjacent cell in 1 cost, so cost incurred is 1. I reach to 3 comma 4. Now from 3 comma 4, I can go to 4 comma 5 in 1 cost, which is a special path. So 1 plus 2 plus 1 plus 1, 2, 3, 4, 5. 5 is the minimum cost right here. Now you will say, Aryan, how you showed it's a minimum cost? I never told that it's a minimum cost. I just showed you, okay, it is one such path you can take. But now the problem is, how will you take this path? Let's look at the next example pretty quickly. It's also same that we can just, if you just see, if you just look closely at these particular cells, so to go from 3 comma 2 to 3 comma 4, this standard cost incurred standardly without using the special edge, it would be nothing but 2. But he's giving you cost 4, so never use it. From 3 comma 3 to 5 comma 5, the standard cost incurred would have been 4, but he's giving you 5, which is more. Don't use it. From 3 comma 4 to 5 comma 6, the standard cost incurred would have been 2 plus 2, which is actually a 4, but he's giving you 6, so it's also not required. So all these special edges are not required at all. I just have to go from this particular target, from this start node to this target node. What is the cost incurred? I will not use any of these special edges for sure. No worries. What is the cost incurred? Nothing but 7 minus 2, which is 5, and 5 minus 3, which is 2, 5 plus 2, which is 7. 7 will be the cost incurred, because now I cannot use any special edges. That is what we have to do. See, what we have to do is, now you will say, Aryan, what I can do is, I will just, as you showed me above, I'll just make this entire matrix, and I'll just make the edges from every node. See, what I can do is, the standard thing which comes in your mind is that, okay, I can make this entire matrix, and what we can do is, I know, okay, from this cell to the next cell. See, in a matrix, if you have just done a traversal, if I have just tried the traversal in a matrix, how we can do? We can move left, bottom, right, top, all that stuff, right? Same. I can attach this cell. I can just say, okay, your movement, it can be right, down, left, or top. It is, and the cost incurred would be nothing but 1. But the new thing comes here is, I can also go from one cell to some of the non-adjacent cell. Let's say the cell right here, the cell from 1 comma 2, I can reach to 3 comma 4 with a new cost of 2. So standardly, what we assumed in a standard traversal would always had been, okay, to move adjacent cells, the cost required are always 1. But now the cost required is actually like earlier I had 4 options to add a node. Okay, I'll just not remove it. But yeah, for this I had 4 options, which means the neighbors were only 4. Right? For a cell I comma j, the neighbors were only 4 earlier. But now I can say, okay, I have some new neighbors also, which are the special neighbors. And every neighbor has a cost. Earlier the cost for every neighbor was 1, but for the cost for special neighbors are nothing but Ci, C1, C2, and so on. I can make this graph and I can just try to traverse it and just try to reach from my source node to my destination node in my minimum distance. You saw what happened. If you just make this graph out, and ultimately the graph is made. Every graph edge has a weight. How you saw it? Because you saw the graph edge had a weight with it. Ultimately, you had to reach a final graph. Remember something. From source reaching to the final destination, you needed to traverse, reach from source to final destination in shortest distance. That is nothing but our Dijkstra's algorithm. That is how we got the intuition. Okay, I just can build the graph out of it because earlier for standardly for me, but before that, folks, just smash that like button. Yeah, you guys not liking it, but yeah, what we're saying was that if I'm starting from a node, earlier as the standard graph traversal, as a standard traversal in this matrix grid, I had 4 options: go left, right, top, or bottom. But now because of the special edges, I have some special options to go to. So now my neighbors, it can be more also. But now earlier when I had only adjacent traversals, so weight was 1 for everyone. So I was never considering the weight to actually write in my answer. But now the weight, it can be 1 is for sure, but it can be C1 also and C2 also. So I have to write the weight for everyone. Now my ultimate task was to go from source to this destination in the smallest distance. That single source shortest path problem is nothing but R Dijkstra's. From single source, I can find the shortest path to all the other nodes, but I'm only concerned about the node D right here. And by this I can find, okay, what is the, how from this S, how I can reach my D. Now comes the interesting part. Okay, now you got to know, okay, what we can do is we can build the entire graph. We know the graph can be made from one cell. I can move to adjacent cells, left, right, top, bottom, and I can also have some special edges. But I'll just ask you, can you make this graph right here? You can see, okay, Aryan, you made an n cross m matrix, but I'll ask you, is it even possible to make this matrix? Let's look at the constraints once again. See, your start and end, it can be 1e5, right? Which means I can have my start and end as, let's say, 0, 0, and my target start and end as, let's say, 1e5, 1e5. Can you make a matrix of this size, 1e5, 1e5? No, right? That is the reason. One thing for sure, you cannot build a graph out of this entire matrix. You have to think something smart. Think something smart. Which means, I just want to say one thing. What I mean by not building the entire graph is, you can't choose to go to adjacent cells at every point. Which means, if I'm standing here, sorry, let me change the color. If I'm standing right here, so although I have some special nodes which can reach me here, but what I was considered earlier also that, okay, I will go here, I will just try to go here, I'll try to go here, I'll try to go here. So I can have multiple paths. Okay, you can have multiple paths, but it is not that you can just traverse everything down. It is not possible. So how it will be possible? Is it possible or not? Let's look at with the diagram. Let's imagine those special nodes as these, right? I will just name them as U and V, right? U and V. Now U and V. Now U and V. It is the special nodes. From U to V I can go. Remember one thing. Just remember one thing. Just remember one thing. What we have to remember. Special nodes can take you from x1, y1 to x2, y2. It is unidirectional. It is unidirectional from x1, y1 to x2, y2 and not vice versa. So special nodes can only take you from U to V, from U to V, from U to V. Let's say I have this special nodes U to V, U to V and U to V. Now my main task was what? To start from this node, let's say start, and to end to this node which is target. Let's forget for now that we have these cells, which means we have these cells as the coordinates I, j. Let's consider for now that, okay, I have one node and it is two nodes, it is two nodes. I have to just go from one node to another nodes. Now, why we actually had to consider this particular gaps, which means you remembered one thing, why we were saying, okay, that I have to go, I can't, like, it's not necessary to actually go on to these special edges. We can actually go on directly also, as we saw in the example too. It's not necessary to go on the special edges. We can go directly also, right? So we have one option. Either we can go directly or we can use the special edges. Right now, many people, what they think is that either or came in, so it's a DP problem. But you remember one thing, this either or came in after we searched, okay, after we had found already that it's the Dijkstra's problem. So that progress, that intuition part, okay, how you move on to step by step, That is how you actually build, okay, which algorithm is going to be applied here. Because many people just think, okay, either we will grab this edge or we will not grab this edge. Maybe it is benefit or like good to grab this edge or not. That is like what you will get as wrong answer, or probably if not wrong, then a DLE. That's the reason that how we actually build. Okay, now we have two options. Either we can choose to use these edges, or we can directly go from source to target. This is the same thing what we can do. We had one options. Either we can just go directly from here to here, or we can just use these. Now, how to use these, Aryan? I never know that I can go from here to here, or here to here, or here to here, or here to here. I can't, right? So I will try everything out. I will go from here to here also. I'll go from here to here also. I'll go from here to here also, right? But Aryan, what if I don't need to go at U? Let's say I need to go at V directly, and from V, let's say it is matching, and from here, let's say I directly want to go. You are saying right. From start, it's not necessary to actually go on to U only. You can go on to V also. From that V, maybe you are going to U. That can be super possible. That is super possible. So what he can do is, you can just go from S to V also. You can go from S to this V also. You can go from S to this V also. Maybe it's the reason. Maybe it is possible that from this edge you have some other edges which can actually you can get from other U also. Now, I'm just thinking brute forcefully now. Okay, what all edges I should consider? I'm not considering that, okay, I should choose this, I should choose that. I'm just considering, okay, I'll choose everything which is right now with me. Why I'm choosing is because I know one thing. My special rows are just 200. Just 200. Even if I get all the pairs of special nodes and all the edges, then still it won't go maximum like 200. Even if it goes 200, even if it goes 200, still it's 26. Although your will just finish at 200 or 200, but still you can see you have a high capacity to actually increase your complexity. So I'll just not think more. I'll just try to place edges so that I can know I can traverse every edge. But it is what we did for our S, but the same can happen for T also, which means our T can come from here, our T can come to here, our T can come to here, or maybe I can just directly go from here to here. I can just directly go from here to here. I can just directly go from here to here. That is how you can make the graph. But Aryan, I could see one thing. I could not see first, like before, yeah, you guys, if you are not sane, just be insane. And please, smash that like button. Let's reach to 40 likes. But while we are just seeing how we are building our graph with these edges only, is it finished? Are we finished building the graph? Yes or no? No. What we can also do is we can also move from this particular V to this U. Right, from this U to this U, this U to this U, and as these pairs are just 200, so I can just have that O of n square thing, that okay, I can just go from here to here, here to here, and here to here I'm already going, right? Also I can just go same for V here to here, V here to here, V here to here, V here to here. I can just make the edges out of, ultimately what I'm doing here right now, you can see, is from this source to this target with these edges in between. I am just trying to place every edge, whatsoever edge is possible. And how I'm so comfortable in placing the edges, because I know these are nothing but 200. So even if I just place every edge from every other edge, because see, if it is 200, so number of pairs, number of nodes, it can be 400. 200 plus 200, right? It can be 400. For every node, I can have 400 options, let's say. So 400 into 400 will be the number of edges for this only. And then for the source and target, I will have nothing but again 400 edges. And again 400 edges for target. So in total, 400 plus 400. That's all the number of edges which I will have. And that's how I can build my graph. And now, okay, my graph is completed. See, every edge I know what is the weight like. For this edge right here, for this edge right here, we know what is the weight. You know what is the weight? It is nothing but, as it was saying, let's say its coordinate was ti comma tj, its coordinate is si comma sj, so its distance is tj minus sj mod plus ti minus si mod. And the same will go for every edge from this s to this, let's say u, let's say it is u1, so it will have u1 of I and u1 of I and u2 of I, right? Sorry, u1 of I and u1 of j. This v1 will have u1 v1 of I, v1 of I and v1 of j. Thus what we can do is, okay, I will just have, when I add this particular edge right here from here to here, when I add this edge, I will just say, okay, its cost will be nothing but u1 of I minus s of I mod plus u1 of j minus s of j mod. And that is how I can build the edges cost for every node. Now when we know, okay, we have these nodes right here, now it's a standard graph problem. Okay, we have these nodes right here with us. I have some or the other edges, I have some or the other edges, I have some or the other edges, and I just have to reach to my final destination node, which is necessarily target. I have the cost for every node, right? Cost of every node, cost of every node. Thus I can just start a Dijkstra from this start node, and when ultimately I reach this target node T, I just find, okay, the cost, I know whatsoever costs are there, it will ultimately reach to this target node in shortest amount of time. That is how we can reach, by single source shortest path problem, we can actually reach our final node T. And you saw one thing also, the number of edges are also not that large. Thus we can easily do our problem. The thinking part was still easy, but implementation part, you can implement it way cleaner. You can just apply the for loops, but to actually show the granularity at which it was working. So earlier I tried to implement the shorter code by using just for loops and all that stuff, which means going on to all of these pairs. And in this pair also, what will happen is, if you mark, see the edges which are directed were only from u to v. All the edges are, other than that, all the edges are unidirectional because it does not said anything, right? That's the reason you just have to mark from this node S, to this node U. Then again from U to S you will also mark. Then same from U to V you will have to mark, which is for sure unidirectional. Then from this U to V you have to mark, which is unidirectional. But from this S to E you have to mark, which is bidirectional. The same way I'll just keep on going from every node to every other node. And I hope that you guys got the intuition of the entire thing, that okay, how we thought, and now how we thought, okay, why we can't build the entire graph. Then we just tried to place the edges. Okay, how many edges we can place? Is it possible to place the edges? And let's say if the edges are placed, now we can actually run our simple Dijkstra algorithm and we will be good to go. Before that, let's look at the code implementation right now. But before that, if you guys had got the problem and the explanation, just smash that like button. Let's reach to 45 likes and we would be good to go to the code explanation. Let's quickly switch back. Just smash it, spank it. I say spank. How you can spank your phone? Oh, nice question. But yeah, let's quickly see the code. Don't be scared when you see the code. It is a bit more granular in terms of what is happening inside and what all edges are being made. The same code can be written in 15 lines, but maybe you won't be able to grab, okay, how many edges, how many nodes, how many connections are being built. But you can always, if you just write 8 lines, you can just use a for loop and write 2 lines. that is also possible and always possible. So yeah, let's look at the code. As I told you, don't be scared at all. I'll just show you everything out. Now, firstly, I will have, okay, it is not required. Now comes our graph. As I said, I will quickly show, I will also parallelly show, okay, what this thing is. As you can see, graph is nothing but from a pair. See, I'll just show you. Let me change and show you the screen. So basically, in standardly, your graph was from a node to actually the lists of nodes. It was how your graph used to look like, right? Now, in this case, your graph would look like what? From the node I comma j to the nodes I comma j comma cost, because now it is a edge with actually a weight. So it is the cost, or you can weight say anything. Thus, from this, I can just say, okay, I will have a vector of this whole list where everyone will be a pair. I can also have a vector of I comma j comma c, but vector is slow, pair of pair is fast. Thus, I took it as a c comma I comma j, which is pair of one element comma pair of two elements. That is how I will take it, and it's a vector. So basically, your one pair, it maps to the vector of pair of pairs. That is what we have written in our code. If you just clearly see, pair to actually vector of pair of pairs. That is how we can build our graph. Now comes the interesting part. I have the start node, so I just grab the start I, which means, see, every node, when I say, it has coordinates as in I and j. Yo folks, let's reach to 45. We just started off with the code itself, and 45 is still not done. Let's reach there. If you guys liking it, then smash it. Now what will happen is, I will start from a node si comma sj. So basically, I just bifurcated, okay, for this start, okay, what is my start I and start j? I need to reach to this target, which is target I and target j. Okay, cool. One thing we initially saw was that if I just start from this si comma sj and I have to reach this ti comma tj, one possible way is I just go directly. So I will just add this edge from here to here and from here to here, because I just want a unidirectional edge. Oh, sorry, bidirectional edge. That's the reason I will just add both the edges. Now what will happen is, it will have tj minus si sj mod plus ti minus si mod. This is the cost of this edge from start to end. I will try to place every edge possible. Let's see how this edge is being placed. Now, as you saw, I placed an edge from si sj. I hope that the highlight part is visible to you guys also. Yeah, I just saw, okay, this si sj, there's a node. I just have it to ti tj, but the cost is si minus ti plus sj minus tj. Now again, I can have, see, I don't think much. I just try to add edges everywhere possible, because it is what I can do right now. Thus, because constraints are pretty less for me, because I can just try out every edge. That's the reason I just did it. From ti tj, I just went on and just did a, okay, what's the ABS like, and which is the cost incurred, and it goes from si sj, although it won't be required, still if it would pass. Now going on to the next thing. Okay, your SNT, start and target, are just done. Now you have to think of just applying for UV and all that stuff. So for every edge, which means I will just grab, okay, I will start with this node. Let me quickly go back. Now I will start from this node, and these are the nodes. So basically, as I told you, it's a node right here, right? It's a special edge, u1 comma v1, u2 comma v2. Now let's say it is u2 u3 comma v3. What I will do is, I will just go and place an edge for everyone. place an edge, and see, it's a bidirectional edge. It's a bidirectional edge because it can happen that I come from here to here and I can go here, or it can also happen that I come from here to here and I go here. That's the reason I have to place a bidirectional edge. Thus, okay, cool. Now let's say we just placed an edge to everywhere. From here I can also place it to here, and from here to here it is always present, but it's a unidirectional edge. Now we will see every edge how we will place. So you saw what one thing, we starting from one of the edge pairs and I am just marking my edge pairs to every other pair, right? That's the same thing which we will do. Yo folks, let's reach 45. Just one more, that's it. So now what will happen is I just start from this u1 v1. You will see this is the first edge pair which we have R, right? Now what I can do, okay, with this first edge pair there are few operations which I can perform in this edge pair itself. What are the options like? Let me quickly show you guys again. With this first edge pair, before actually moving on to the next step, let me quickly change the color. So it is the first edge pair, right, which is the edge, we have special edge. Now before moving on to actually try and place edges onto the next of the special pairs, there's one thing we can do. We can place the edges from start node and target node also, right? That is what we will do right now. Before actually moving on to the pair bondings, like the next pairs, the next special pairs, the next special edges, I'll just firstly start with this bonding from start to target with this particular edge. So I will just S to U1, S to V1, T to U1, T to V1. This is what I will do right now. I'll show you guys. If you just go, so basically it is from U to S, and parallelly you will also see that I have just placed the weights. It is from V to S. Also vice versa can be possible, from S to U, from S to V. Also from U to T, from V1, which means that I'm considering only one pair right now, from V to T, and also vice versa, from T to U and from T to V. And also you know that one edge also has a special cost. This one edge, although we marked all these pairs, right, and all of these also, from S to V and from T to U also, we marked all of these 8 pairs, but still one more was remaining, which is a directed edge from U to V, which has a special cost as C itself. Now I will just add the special cost also, which is the C cost right here. It is that cost. Now it is done. Now comes the part where the pairs, which was the edge pairs, let's say this pair, this edge special pair, it will be actually gone and mapped, like an edge will be made from this pair right here to the next pair. Thus I will just have, okay, edges from this U1 to U2 V2 to the next U2 V2 to the next U2 V2, and so on and so forth. And the same goes for V also. I'll just apply the same stuff right here. I will just place an edge from U1 to actually U2, U1 to actually V2, and then same from V1 to actually U2, from V1 to actually V2, and the same vice versa also, from U2 to U1, from U2 to V1, and for the next pair, vice versa, V2 to U1 and V2 to V1. Thus, I can just build my entire graph like this. Although you can just write the same code in 8 lines, but it is just to show, okay, how many edges are being made. Now comes the interesting part. It is nothing but a simple Dijkstra's algorithm. If you have not seen the Dijkstra's algorithm, I'll just quickly show you guys. It is like, it's a standard. I usually do like this only. I use the snippets to actually go on. So if you just go and look, it is a standard Dijkstra's algorithm which takes it. So basically Dijkstra works on the nodes, right? But for us, a node is a pair of what? Coordinates. That's the reason. What will happen here is, it just works. Okay, how it is Dijkstra's works? We just take a priority cube which just gets out V edge which has minimum weight right now. Thus, I'll just initially push my source with the initial distance as 0. I just keep on going in my priority queue, grab out the minimum distance, just mark, okay, the current D is so far this much, and it is, I have reached to this node right now, 2 node. If it is already visited, no worries, just continue. If it is not, then just mark my ID and mark visited also, and I'll just move on to its next neighbors. That is the same thing. Now I did the same stuff, exactly same code. It is standard basic Dijkstra's code which I have right now. We'll also see in our bar graph series for the same exact same code, but it is how I will do. But the only difference is in this source, rather than one node itself, I will have a pair, which is I comma j. Now if you will see, I will have a pair to actually mark it as visited or not. I will have a pair to mark it the distance of that particular node. I will have the priority queue exactly same. It's just that the difference, I replaced my this PLL is nothing but pair of long. So I replaced that with the pair of int comma long. Pair of int comma pair of int. Which means pair of, earlier it was only this pair, right? I just have one more dimension. That's the reason I just added this. Now priority queue is made. I'll just push that first element in my priority queue. See, it is a high dimension, which means standardly we are easily able to visualize smaller dimensions, which is like this. It's easily able to visualize, but it's hard to visualize when a few more parameters comes in. So please do parallelly look at this code right here. Have a screenshot of this, have a picture of this in your camera, phone. This PLL is pair of long, and LL is long, anywhere it is written. So just have a snapshot in your phone and parallelly keep on looking at this code of Dijkstra's, because it's sometimes hard to look at high dimensions code. Thus, what we'll do is now we will just go on and check, okay, what is the D, what is the coordinate I am right now. Rather than node, I am looking at the coordinate. If the coordinate is visited, continue. If it is not, just mark that D and visit it, and go on to the childs, just push in the new distance, which is D, existing D, plus whatsoever I have to push that distance. It is a simple Dijkstra's which we did right here, and ultimately we keep on, as it says, single source shortest path, which means it just goes from that single node to all the other nodes and finds the shortest path in this distance map, and thus it will just keep adjusted. Done. Okay, if you have reached this cell comma t of I comma t of j, what is the distance like? And you can just return that distance. That is how you will just return that answer. I hope, okay, I have to remove that particular function right here. I hope that you guys got it, that how we initially thought for this problem from scratch. I know it is a bit hard problem for both thinking as well as for implementing, but yeah, that's the reason I told you I thought it was harder than the fourth question. But it is that when the people start with it, because many people get the illusion, okay, it's a graph problem, I will apply the Dijkstra, but just implementing that same stuff, it can have errors. Thus, maybe that's the reason many people tried on this problem, but they could not complete it. Thus, it is the case. As you can see, many people tried, but they could not complete that. While on the other case, I'm not sure that why it was not the case for this problem, but yeah, it was actually the easy problem than the first problem. Now let's quickly go on to the fourth question. And but before that, if you guys have not liked it, then please do hit the like button. Why bidirectional for start and end? Yeah, for start and end, you can just go the unidirectional. I just like thought of in that way. Just try to add an edge from everywhere to everywhere, wheresoever is possible. But yeah, from end to start, it's of no use. You can just remove that. That's actually will can also result in your answer for sure, because start to end you'll for sure go, but not in that way. Hi Aryan, when I will be comfortable in hard questions? It's just not that particular time when you will be comfortable. It's just that we can just keep on going at the questions. Sooner or later we will actually started seeing the patterns and all that stuff, and as we start seeing the patterns, it's very sound okay. It can be like implemented like this, and as we progress in a problem, no. So it's actually, it feels like to actually work on the problem more. So if we are progressing on a problem, we will actually feel like solving it. If we are not progressing on a problem, we will not feel like solving it. That's the reason. That's the reason I just say, okay, just start with the problems, hard problems, just think, okay, if you're progressing or not, and just keep on trying for the problems, and sooner or later it will be easier for you guys. Now let's go on to the next problem, which is lexicographically smallest beautiful string. But before that, if you guys have not liked that, let's reach to 50 likes. It was a tough contest for that, just motivation for us. Let's reach 50, and so that we can actually build on and solve the problems daily, which means every week the contest occurs and we can solve these problems right now and here. So yeah, I will just quickly go on to the problem, but you have to reach that to 50. Let's go on to that next problem, which is lexicographically smallest beautiful string. What the problem says is that a string is beautiful if it consists of the first k letters of the English lowercase alphabets. Okay, first k letters of English lowercase alphabets. It does not contain, which means I'm only allowed to use the first k letters. I will be given k with me, which means, okay, in this particular string right here, which I'm going to make in future, I can only use those k letters. Cool, no worries at all. It does not contain any substring of length 2 or more, for sure, which is a palindrome, which means I cannot have something like this. A length 2 is also a palindrome, a is also a palindrome. I cannot have something like this. This is also a palindrome. Shall I think of everything else, which means bigger strings also, which means let's say a string of size 4? I will say no. If this is not a palindrome, this is not a palindrome, this is not a palindrome, for sure the entire thing can also not be a palindrome, right? So I can just look for my this thing. Okay, it's a and this ABA. I just look for these two things. Okay, it should not become a palindrome, which means this, if I am just having a character right here, it should not match with this character. If I'm having a character right here, it should not match with the second last character. Also, it should not match with the last character because it is the first condition itself. So to actually simplify this particular statement right here, one thing we can for sure write is that it does not contain any substring of length 2 or more, which means I can only have to consider the substring of length 2 or 3. That's it. Because of this 2 and 3, if we are able to say, okay, this substring of length 2 and substring of length 3, if these two are not palindrome, for sure, no one can palindrome, because as we keep on going bigger, then it should not be palindrome, it should not be a palindrome, it should not be a palindrome. So it will be different, which means it will be C, D. If it is not a palindrome, so it can't be a C. Let's say it is E. If it is not a palindrome, it can't be a C. It can't be a D. It can be something else. Let's say E also. It can be E also. So you can see, still it's not a palindrome because C and D came in picture, and it was because of the reason that we have this condition that our two sub-array size, it can't be same. Cool. Now one condition we get to know, okay, it's simplified condition, we get to know, okay, how we will find, okay, if substring is palindrome or not. Next thing which the problem says is that you are given a beautiful string S, which means the string S given to you right here is also beautiful. How? What is the beautiful condition? Condition was that it contains the first k letters and also no substring. When I say substring, I will just look for the size 2 and size 3. Substring is a palindrome. Cool. So I'll just go and look. Okay, it's a beautiful string. How? It is C. A, B, C, Z. As you see, it's not a palindrome. Cool. 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 Yeah, that is a beautiful. And the K allowed is 26, so we can do anywhere we want. Now comes the interesting part. Return the lexicographically smallest string of N, which is larger than S. Lexicographically smallest, but larger than the given S to us. S is given right here, and is beautiful, which means it should be larger. It should be larger. It should be lexicographically smaller than this particular S, and also it should be beautiful. which means this condition right here, that I can only have the alphabets K, first alphabets, and also the substring should not be a palindrome. And we'll only check for 2 and length 3. That is, there is no such string, then return empty. If I could not find any such palindrome, like let's say if I just say Z, 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 K is let's say 26. Can you find anything larger than this, which is lexicographically smallest? 26. It's already done. It can't have. So that's the reason I can just have a empty. As in this case only, we can have fourth stuff. So DC, the next bigger thing, it can be either DD only, because 4 is allowed maximum, which means A, B, C, D is allowed. I want bigger, so I will just place it bigger, D. But still, DD is a palindrome. It is not a beautiful substring. Answer will be an empty string. Now, it is just saying, okay, what's lexicographically smallest string? Lexicographically smallest is that, okay, next element which comes in different is actually a bigger element. Then it is lexicographically larger. Before that, if you guys have not liked it, then please let's reach to 50 likes. We are solving 2 very good questions of this contest. We have solved problem 3 and now we're solving problem 4. That was really good. So now we saw, okay, for this problem right here, A, B, C and Z, the lexicographically smaller, lexicographically larger, which is smallest. Like it should be just lexicographically smallest but larger than S. So larger than S but lexicographically smallest. A, B, C. Now after Z I can add anything. Let's say if I add a D, oh, it's lexicographically smaller than. So for this C I need to increase it. I will increase it by D. Now I can have Z here. Why Z here? I want lexicographically smallest, right? Add a here. Thus I will have my ABDA as my answer. And as we go on to this example, it is exactly what we have to do. Exactly what we have to do. What? C. Exactly same. I'll just take this example only. Which means I have this A, B, C. What was the problem? A, B, C, Z. Now one thing for sure. I need to make this as larger S. As S is larger. But it should be lexicographically smallest of what is possible. So for sure it's of no use. See, to actually make this larger of S, I will increase some character of this particular string S, A, B, C and Z. So to get this larger, I have to increase a character. I can increase this A to B, I can increase this B to C, I can increase this C to D. I can't increase my Z, but yeah, no worries. What should we increase? This particular first one, second one, third one or fourth one? Fourth one we cannot increase for sure, yeah. But yeah, out of these 3, which one we should increase? Tell. Which one we should increase out of all these? If we want it, you see, one thing is larger. For larger, we have to increase for sure. For sure we have to increase. But I am asking which one I will increase. This or this. If you just have a thought, you can increase any one. Which will you have increased? First, second, third. Tell me. No one is listening. What happening? Lag is not that much only. But yeah, still, like meanwhile you guys give the answers. Firstly, let's reach the 50 likes. Just one more if you guys liking it. And also, please write down which one we will choose. For sure, we will choose to increase this one. Why? Because if we just increase like this B, then it is not the smallest lexicographically string. Which means if it is increased, let's say, if you had increased your A to B, then it would have become B, B, C, Z. Third one, correct. That's correct. Because if you have increased this A, then it would have reached to B. Now, Ashish gave the correct, Akash gave the correct answer. No one else is listening, I guess. Oh, Ankit also. 50th like is mine. Let's go. Dhruv, third. Yeah, correct. That is the reason. Why? Because we want lexicographically smallest string of length n. Thus, if we just have increased our first character B, B, C and Z, B, B, C and Z, else, what if we have considered to increase the third character, which is A, B, D and Z, then you can easily see this one is lexicographically smaller because these are smaller ones. When we see lexicographically smaller or larger, we start from the left itself to actually look at this string. okay, it's smaller, it's smaller, it's smaller, it's larger, also larger. That's the reason. What I can do is I will try to actually, I have to make it larger. So one thing I was sure I have to increase the character, which means I have to increase this C to D or something like that. I also want the lexicographically smallest, so I will just increase that from the left itself. Okay, I just get to know one thing, I will increase it, I will increase from the left. Now, what is the next thing? Let's look at back. I will try to increase from the left itself. But, I just know, I will increase, but from the left. But, one thing was, to make it beautiful, one thing you need to make sure. Firstly, you can only increase the characters up till that they reach that K limit. So if I just about to increase it, let's say the example of DC. So if I am about to increase it, I can increase it to D. No worries. Because K was up till 4. I cannot increase it more to E because K was up till 4 only. Right. That is one thing which I need to consider while increasing an element, that I can increase that element up till K limit only. That is one condition for sure. Next condition would be, sorry, I spoke loudly, but next condition would be that, okay. Next condition was, it should not contain any substring of length 2 or more, which is palindrome. And we saw 2 or more palindrome. We can only check for 2 and 3 length only, that is required. So I'll also make sure that when I'm increasing this particular character right here, it should not become equal to the last character, and also it should not become equal to the second last character, which means if let's say it would have been an A, let's say if it would have been an A, and I would have had an option to increase it as much as I want, let's say 26. So if I would have increased it to B, can I increase it? Can I increase it? Tell me, can I increase it? No, for sure. Why? Because it is same as the last second alphabet. So I can't increase it to B. For sure. Okay, let's try increasing it more. Increasing it to C. Can I do it? Can I do it? Yes or no? No, we cannot, because it is also same. So the condition 2 which was there, that it should not, the string of length 2 or more, it should not be palindrome, that will get violated. No worries. We can't increase to B. We can't increase to C. Let's increase it more. We can increase to D. Cool, we increase to D. Now what will happen is the result will be nothing but D. Okay, change color, change D. So basically instead of A, I can increase it to D. That will be the larger string than S, and also lexicographically smallest, and also following the condition that K limit was there, and also I am not having any palindrome. These 4 conditions we have to meet, and it is the only problem which we have to consider, that okay, only these 4 conditions should satisfy and we are good to go. We are good to go. Let's see what will happen if let's say I would have said, okay, hey, you can't, you can only reach to 3 characters. What would you have done? Which means, let's say it's 3, but for meanwhile, I'm just saying, okay, let's say you can only reach to those, or what I should say, let's say it is D. It is D, right? And it is C, and it is B. Cool. Or I can say it is as D, or it is as A. Let's have it that only, but I will just modify this example while I am iterating on the example itself, that okay, now the condition is that your K can at max go up to 3C, right? Which means you can increase that A to B, then you can increase that, okay, you increase that, sorry, it was, I guess, B, right? It was, and it was C. So you can increase to B, cool, no worries. You can increase to C, no worries. Can you increase it more? Can you increase to D? K is 3. You cannot increase to D. Now you will just move back. Now you will just move back. Now you will try to increase this. Okay, let's see if you try to increase to D. Can you increase it? You cannot. For sure you cannot. Thus, okay, D cannot be done. No worries. Just try to move back again. Now, can I increase it to C? Can I increase it to C? I'm asking you guys, can I increase it to C? Yes or no? Nope. Why? Because it is palindrome. I need to make check. Oh, it should not be a palindrome. So I'll just try to increase it to D. Can I increase it? Can I increase it? Can I increase it? No, because K is 3. Cool, no worries. Just move back again. Now what I will do is I can increase it to B. Can I increase it to B? No, the next one is already a B. I cannot increase it. Can I increase it to C? Maybe I can. Maybe I cannot. What if I can increase it? What if I cannot? What if I increase it to C? Now I know, okay, I can increase it to C because I cannot increase it to B. So B is never an option for me. I can increase it to C. Oh, I increase it to C. So shall I return this answer? Shall I return this answer as C, B, C, A? Is it the smallest palindrome? Yes or a no? Is it the smallest palindrome? Sorry, smallest, lexicographically smallest string. Because I was just trying to move back and trying to increase every letter, but every time the condition was not satisfying. Either it was not satisfying the condition of K, or it was not satisfying the condition of my back character, or it was not satisfying the condition. Okay, that's I-1 is same or I-2 is same. That was not satisfying at all. So what will I do? Like, okay, I just keep on moving back. I reach at the back. I reach the back. Shall I increase it? But if you just remembered one thing, when we were actually moving back, from our A to C, then I was just comparing my A with my C and B. I was trying to increase it. I was trying to increase my A to B and then to C. Okay, no, B can't go and C can't go. No worries. I just tried to increase my C to D. It can't also go. I just tried to increase it to C. Can I increase it? It is the question which you guys missed. Can I increase it? Yes, I can. Why? Aryan, you can see it is a palindrome. Like it is a palindrome. Nah. We will only check backwards. Why backwards? Because we can actually modify the forward string later, which means I can increase this to C because the last character is not a C and last second is not also present. But if I just modify this as a C, now it becomes AC. But as I modify this to C, I can actually modify my forward array to be a lexicographically smallest one, which means now I can just modify this as A. Can I place A? No, because see, now I just try to modify this A. Okay, it remained A, it is C. Now I just tried to again modify my forward string again. When I tried to modify it and C, it can come. Why? Because the last letter was A, it is not C, and the last second it's not even present there, but it is right here, which is this C. I will try to change it to A. Start from the scratch, modify it to A. Can I place it? Because last second is A. I cannot. I'm always looking at the last second because I have the liberty of modifying the forward string. That is, while checking for the palindromic condition, we should check for the same character or not only in I-1, I-2 possible, but also in I+1, I+2 position, right? No, that is what I told. We don't have to check for I+1, I+2. We only have to check for I-1 and I-2. Why? Because we can actually modify our I+1 and I+2 when we actually modify this I. If I modify this I, anyhow I can modify my I+1 and I+2. And no matter what whatsoever. How? Let's see. I can modify this C to A. Can I modify it? No, because it is same. I will modify it to B. Yeah, I can now modify it to B. Now it became a B. Now as it is B, next I will just try to modify it again. Can I place a? Last it is same, last no one is same. Yeah, I can place it. It is the lexicographically smaller string which is larger than the string S. That is the reason I said we don't have to check for I+1 and I+2 because I+1, I+2 I can later modify by myself because I want lexicography smallest, so I will just try placing. As soon as I increase this, as soon as I increase my I will just place next I. As soon as I increase my I, now it is entire liberty of changing the entire right string from scratch. I can start from scratch, A, both of them, then A, B, then A, C, then A, like this. I have an entire liberty of modifying the right string because ultimately I have made my string as larger. By modifying this SI to C, string has become larger. Now, the entire right part is in my hand to make it lexicographically smaller. So I will just try to make it as small as possible, which means I'll try to bring from A. I'll just say, okay, is A possible? No, A is not possible. I'll try for B. B possible? Yeah, possible. Then I will try from A for this location. Possible? Yeah, possible. Now it is the lexicographically small string which I need to return. That is how we will do. If you guys got the intuition, got the problem, just smash that like button. Let's reach on to the 60 likes. Or if you guys have any problem, anything which you didn't get it, then please do write down below. I'll just quickly go on and read that comment, and then we will go on to write the code. But yeah, before that, if you guys have any problems, anything, any doubts, just write down that below. It is what you thought, right? You had 4 conditions in your mind. You have the characters A, B, what was that? A, B, C, A, right? You will move from the back. You will try to increase this character. You will move from the back, one condition. You will move from the back, try to increase this character, second condition. Try to increase this character such that it is less than the K, which means less than the K possibles. And also it is a third condition, less than the K possibles. And third condition was also when increasing, make sure to compare from I-1 and I-2 only, not from +1s and +2s, because we can always modify my right part. Whenever I just modify this part, let's say I modified it to D, then I can always start modifying my right part. And I always have to modify my right part because I want the lexicographically smallest. So I will try placing from A. If it is A possible, then I'll try placing the next one is A again. If A is not possible, then I will just try again with B, and so on and so forth, because I want it to be lexicographically smallest. So it remained intact, it increased, it need to decrease to actually make it lexicographically smallest. So these 4 conditions you need to make sure while writing the code, right? Cool. I hope that you guys like it. A little bit greedy, like modifying process, correct? That is correct. So yeah, let's move on to the code. But before that, please smash that like button. Let's reach on to 60 likes before we actually start seeing the code. Code is pretty short and simple. As we said, we will just go on from the end to the first character. Why? It was because of the condition that I want my string S as larger. So one thing I know, I need to increase my S of I, but also it needs to be lexicographically smallest. So I need to go from the back itself. Okay, when I move from the back itself, I will increase. Got it. Awesome, Avinash. Awesome. Avinash, okay, awesome, Avinash. Then as I need to increase my new string S, and because beautiful string S which I need to make right now, it should be more, so I just increasing that string S. Now I'll just check, okay, if that what I increased my character to, let's say, A to B, so is it valid? When to check the validity of this, we had 3 conditions, right? It should be in the limits of K. It should not be a palindrome, which means it should not be same as my I-1 and it should not be same as my I-2. That is the same thing which I will do. It should not be is valid. We'll check. Okay, it should not be equal to my I-1, which means S of I, which I've increased right now. It should not be equal to my I-1, and also it should not be equal to my I-2. This I is less than 1 is just that we don't access any pointer, which means, see, if I do a I-1 or I equal to 0, then it will do a -1 indexing, which is not possible. That's the reason I just placed the OR condition, that okay, for OR, it will not even go at this right locations. It will just check, okay, if that last location has the same character as my current location, which is S of I, has the same character as S of I-1, or if S of I has the same character as S of I-2. If it is any other case, I can't place that. I can't. So basically, I see we have not equal to, so it's actually that If any of this is not the case, which means I can place that, so it's a valid location, which means it is not the case. So if it is not valid, then I need to again increase my S of I. As you saw, we saw right here that we were trying to increase our A to B. Then we check, okay, if that is valid or not. Valid means it should be in the limits of K, and also it should not have that palindrome thing. I minus 1, I minus 2. It should not match. If it is doing great, I'm good. Now, as I said, it should be in the limits of K. It is the condition we will check. Okay, we just keep on increasing. No worries until my palindrome things it gets resolved. But as soon, can't see the code. Oh, god damn. Sorry. Sorry. Really apologies. Thank you, Akash, for letting me know that the code was not visible. Let me go again. I don't know how I missed that part, but yeah, let's quickly see the code again. Really apologies for the code not being shown. I hope that the code is visible now. Yeah, it is. So basically, what we do is, firstly, as we know that we need to go from the back. As we want lexicographically smallest string. We will increase because we want the larger string than S. Now, as we go on increasing, we know to check two conditions. First one being that as we are increasing the character, it should not become a palindrome, which means S of I minus 1 should not be equal to S of I. If I'm increasing S of I, so S of I should not be equal to S of I minus 1, and S of I should not be equal to S of I minus 2. We need to make sure while increasing. So while increasing, I will just check. I increase it, I will just check, okay, is it valid or not? Valid will just check. If S of I is not equal to S of I minus 1, it's valid. S of I is not equal to S of I minus 2, it's valid. Both cases, it's valid. But if it is not valid, then again I have to increase my S of I. I just again increase my S of I. Now, as I said, increasing was one of the conditions, but ultimately you also need to check that your increased number should not go beyond your K allowed digits, K allowed characters. So I will check, just have the check. If my S of I which I have increased, if it is in the conditions of my K, which means A of A plus K, it is less, right? So if my K is 3, it will go to A, B and C only. That's it. If it is the case, now I am sure, okay, I have placed a beautiful smallest character at my ith location. As soon as I place a character at my ith location, now my task is to actually modify the string after, which means I plus 1, I plus 2. Now I have to make it lexicographically as small as possible. It is what we will do right now. We will modify the forward string, which means from J equal to I plus 1 to end. Before that, if you guys have not liked it, then please do smash that like button. Let's reach on to 60 likes. It's just two more of you guys can just smash that, spam that, and we can reach that way. So basically what we do is, okay, I have modified my S of I location with the best character it's possible. Now I have the liberty of modifying the right part as much as I want. I will just modify the right part as much as I want. So I'll just try, okay, right part is I plus 1 to less than n. Then I'll just go I plus 1. I'll try to place the character at I plus 1 starting from A itself, because I want lexicographically smallest, which means I'll just quickly show back the code again. As soon as you saw right here, right? As soon as you place your one character right here, you will try placing the next character as A, if it is possible. Not cool, B, because you want this as to be lexicographically small as possible. That is the reason. What we have to do is we have to just start from the A itself and just keep on increasing until it is not valid. By this, what will happen? And see, you will say, Aryan, you are saying until keep on increasing while it is not happening. What if it just goes beyond your K amount? It will not go. Why? Because if you just clearly look at the condition, then your K will start more than 4, which means you will have always 4 characters to actually verify. If I modified S of I modified. Let's say it is A, right? S of I minus 1 was, let's say, B. It is, I'm about to modify. I place initially S of I plus 1, I place initially a A. It is not equal, it is equal to A, it's not valid. S of I placed it to B. It is equal to S of I minus 1, it is also not valid. I can place it to C. It will not be equal to any of these. And thus, it will be valid. It will for sure be valid. Because I can always place, I have at least 4 characters to place anyhow. So I can place a C right here and I would be good to go. That is how you will make the lexicographically smallest string, which is not a palindrome. So what you will do is, I guess the screen is visible. God damn, the screen is again not visible. Cool. What now we will do is that I will just go on from I plus 1 to actually the end. At every step, I'll just go and check, okay, if that S of J is, I'll just try to place A. If it is possible, if it is valid, I'll just keep on increasing. If it is not valid, I will just keep on increasing it until it becomes valid. Ultimately, I just increased. It is valid. I can just return a S. Maybe in worst case, I just tried everything out. Maybe it is becoming a palindrome again and again. Maybe it is having that particular, K limit exhausted. So ultimately I have to return an empty string as we saw in this particular code right here. Right here, yeah, it's visible. So yeah, that is how we will just go about it. As you can see, the complexity is pretty small. N is 1e5. Let me show the complexity right here. For this part, you are going on N. N is nothing but 5. For every of those N, in worst case, you can increase that character to K times. K is nothing but 26. So N into 26 for this particular thing. As soon as you have increased that character, it is now fixed. Now your now your largest number you have found. Now your ultimate task is to make it lexicographically smaller. You have found a larger number, which is beautiful. You have found the larger number, which is beautiful. Now it is your task to make it smaller. So as soon as this N into 26 is done, then only in one of the conditions it will happen. Only in one of the conditions. Remember, it will not happen for every time. It will happen on only one condition. How it will happen? It will just go back again on those N elements and will try to increase those. So that is O of N into 26 plus O of N into 26 in worst case. And that is how our complexity will go off to O of N into 26 only, and that's it. That's how we can solve this problem. I hope that you guys liked it. If you have any other questions, any other doubts, and yeah, meanwhile, if you have liked the stream, just please smash that like button. Let's reach on to 65 likes and I will be super happy. Like legit, my voice is gone, legit gone. Last night also we had a stream. That's the reason, like, you might be seeing a bit low energy right now. It's because the voice is completely dead right and now, but still no worries. You will still shout, still have the energy, still because of love of you guys. That was awesome. Love. But yeah, if we can just reach 65, and yeah, meanwhile, if you guys have any other questions, any other doubts, any other things, I will just take on those questions. Meanwhile, I had one person asked one doubt, which I said that we can have it at the end. What was that doubt? If that guy is still here, or or if you guys have, can you please explain the complexity again? Cool. So basically what will happen is this thing, it can go at max up till the size of my particular S length, because it is iterating on the entire index from the end itself. For every index, I have K options to increase it. Let's say every character is AAA. So you can increase that character up to Z only, right? So I have the ability to increase that character to Z. Although it will never reach to 26 in 4 steps only, it can be either yes or a no. Because for sure you can only compare the last and the second last. So it will be always, in worst case, it will always be O of N into 20, N into 4. Because it can at max go up to 4 steps. But still, while considering the worst case also, let's say if it goes on to maximum limit, it can go, still it can go up to 26 only. But actually it will only go to 4, at max 4 times it can go. Because ultimately it is checking for the last character and the second last character. That's it, right? Now, as it is done, as we check, okay, it is in the limit or not, then we check, okay, if it is, I will just go on and iterate on the next and see this particular step right here will for sure happen only once in this entire array. As soon as it is done, we can just say, okay, it's good. So this one step will be done in only once. Don't consider it will happen every time for this entire array. It will happen only once, right? It's same, exactly same. I'll go on to those n characters after my I and just try to increase that. Still, again, it can go at max of 4 times, but yeah, in worst case, let's consider 26, but still, at max it can go to 4 times. So it is nothing but O of n into 4 plus O of n into 4. That is ultimately complexity is O of n into 4, which is 4n, which is nothing but O of n. That is how we can do this problem. Understood? Thank you so much. Thank you, guys. If you guys have any other questions, we can have it. Else, we will end the stream at 12:55. A 5-minute chit chat. Aryan, OP, Akash, Pama, thank you, bro. Thank you. Just that before leaving, can you guys quickly just have a sweet chummy like at the like button? Just kiss it, smash it, XYZ it, do whatever you want. Genius. Wow, that's a good genius word, by the way. Genius got it. Awesome, got it. Thank you. So thank you to folks. Shalini, Akash, Genius, Rahul, Varun, Avinesh, Akash, something written in other language I can't read. Dhruv and Suraj, Shalini, Ahmed, Mak, Girish and Akash, Vallabh, Hinge. I don't know if I'm pronouncing that wrong, but yeah, thank you so much, folks, for joining in and having the discussion. I'm just reading all the names, whatever it is. Bennett and Saket, anything. Okay, that's nice. MS Darshan, Pratham, Mani, Avinesh, Suraj, Shanka, and Udit. Thank you so much to these guys for joining in, and that is all from us. Let's end the stream. That was so much beautiful talking to you guys, and that was a big contest. Bye bye, Suraj. Thanks, Nishan. Oh yeah, Nishan, thank you for joining in. Pranshu, yeah, bye. You are great. Thank you, bro. You also guys are awesome. Before leaving, if anyone have not liked before, not yet liked it, yeah, see you next week. We have the contest next week on Sunday, so we will have the live stream at 11:30 or 11 whenever is comfortable, but 11:30 is the max. If I have to leave, let's say 11:30ish or around, I just prepone it 11. That's it. Either it will be 11 or 11:30. That's it. So yeah, thank you so much for joining in, and see you guys in the next video. Then goodbye, take care, bye. But yeah, before going, if you guys can please hit the like button, smash it, spank it, do whatever you want to do. Just get that to 65 and we will be good to go. That increase, that was lovely. Thank you so much, and I know it won't increase now, but yeah, cool. See ya.